Welcome to my channel Ganit Matrix. Now here we are going to discuss the topic Jacobians. The definition: the Jacobian of u comma v, right, where this u and v are functions of xy. If u and v are functions of xy, then the Jacobian of uv with respect to xy is denoted by dou of uv by dou of xy. And this is the second order determinant. Ux means dou a by dou x, uy dou u by dou y, vx means v with respect to x, that is dou v by dou x, v with respect to y, that is dou v by dou y. By finding the second order determinant by AD minus BC, so we will get the corresponding Jacobian. The second one, the reciprocal property. The reciprocal property says whenever you have a Jacobian, right, dou of uv by dou of xy, multiply with its reciprocal, means 1 by j. If j is dou of uv by dou of xy, its reciprocal is dou of xy by dou of uv, then corresponding product equal to 1. So the reciprocal property says the product of the Jacobian and its reciprocal is always equal to 1. The third one is the chain rule property of Jacobian. So here, right, dou of uv by dou of rs, right. Here u and v are functions of xy and x and y are again a functions of r and s, then dou of uv by dou of rs equal to dou of uv by dou of xy into dou of xy by dou of rs. And remember that for defining the Jacobian dou of uv by dou of xy, u and v must be functions of x and y, then only the Jacobian is defined. And this is the important determinant, right? Since suppose you have 3 by 3 determinant, if we have Jacobian of functions of 3 variables, okay, uvw with respect to xyz, dou of uvw by dou of xyz, so in that cases, right, or if the determinant involves complex terms, we always expand the row or column containing the maximum number of zeros to minimize the calculation errors. That means we make any row or any column by using some row operations or column operations or some manipulations, some algebraic manipulations. We make any row or any column containing as a maximum number of zeros and expand with that by row, expand that determinant by that row or that column gives the final result, and the final result must be accurate, which is complex free. Next, there's a quotient rule that says whenever we differentiating f by g, then remember that differentiation of f of x by, this is the quotient rule of differentiation, right, v dash minus uv dash by v square is g of dash minus f g dash by g square, right. And this is the first example. If x equal to r cos theta, y equal to r sin theta, find the Jacobian dou of x comma y by dou of r theta. And here also how this Jacobian is defined whenever this x and y must be a functions of r and theta. Since already it is given x is a function of r and theta, r cos theta, y is also a function of r and theta, right. Now first, the Jacobian is dou of xy by dou of r theta equal to, right, x with respect to r, x with respect to theta, that is dou x by dou r, dou x by dou theta. Next, y with respect to r, y with respect to theta, dou y by dou r, dou y by dou theta. Now partial differentiation with respect to x. So with respect to r, we treat theta as constant, right, dou x by dou r is cos theta, right, and differentiation of r is 1. Similarly, with respect to theta, r as constant, so dou x by dou theta is r constant, differentiation of cos theta minus sin theta, so this is minus r sin theta. Similarly, partial differentiation of y with respect to r, dou u by dou r equal to sin theta, and with respect to theta, dou u by dou theta equal to r cos theta. Now construct the determinant, right? So j equal to, so dou x by dou r, dou x by dou theta, which is cos theta minus r sin theta, right? And dou y by dou r, dou y by dou theta, which is sin theta r cos. Expand the determinant, ad minus bc, cos theta into r cos theta minus r sin theta into sin theta, which is r cos square theta plus r sin square theta. Taking r common, r into cos square theta plus sin square theta. So by trigonometric identity, cos square theta plus sin square theta equal to 1. This gives r. The second problem, and so here so we have a function of three variables, right? U equal to x plus y plus z, and uv equal to y plus z, uvw equal to z. Then evaluate, remember that, evaluate dou of xyz by dou of uvw. So for defining this Jacobian, x must be functions of uvw, y must be a function of uvw, or z must be a function of uvw, right? So that is why from these equations, u equal to x plus y plus z, from these equations we can find xyz, we can find the expression x in terms of uvw, y in terms of uvw, z in terms of uvw. See, from the third equation itself, z equal to uvw. Use this, reverse back into the second equation. So y plus z equal to uv, so this is equal to y equal to uv minus z. So this is uv minus uvw, uv into 1 minus w. Now from the first equation, x plus y plus z equal to u, this implies x equal to u minus y minus z. So this is equal to u minus uv into 1 minus w minus z is uvw. So x equal to u minus uv plus uvw minus uvw. So this is u minus uv, this equal to u into 1 minus v. So x equal to u into 1 minus v, y equal to uv into 1 minus w, z equal to uvw. So therefore calculate the Jacobian dou of xyz by dou of uvw equal to same thing, the formula dou x by dou u, dou x by dou v, x with v, dou x by dou v, x with w, dou x by w. Similarly this. Now calculate the partial derivatives, x equal to u into 1 minus v, alright. So dou x by dou u, so with respect to u, v term constant, so 1 minus v constant, differentiation of u with respect to 1. Dou x by dou v with respect to v, u constant, we write u as it is, differentiation of 1 minus v with respect to v. Since constant differentiation 1 0, differentiation of minus v is minus 1, so this is minus u. Since dou x by w, since with respect to w, u and v are constants, so these are zeros. So dou x by w is 0. Since y equal to uv into 1 minus w, therefore dou y by dou u equal to, so with respect to same v and w are constant, we write v into 1 minus w, the constant term as it is, differentiation of u 1. Now same, dou y by dou v, so with respect to v, uw constant, so we write the terms of u and w, u into 1 minus w as it is, because they are constants, differentiation of v 1 with respect to v, right? So dou y by dou w, so with respect to w, u and v are constants, we write uv as it is, differentiation of 1 minus w with respect to w, 1 constant, differentiation 0, differentiation of w minus, so minus uv. Since z equal to uvw, right, so with respect to u, vw constant, we write vw as it is. So we repeat this pattern for dou z by dou v and dou z by w. So with respect to v, uw constant, differentiation of v1, with respect to w, uv constant, we write uv terms as it is, differentiation of w. So compute the determinant, right? Substitute all these terms here, right? Expand the determinant by first row, right? So 1 minus v into, remove the first row and first column, so this is 1 plus minus of minus plus u into, remove first row and second column, write down the second order determinant, right? Expand this, so 1 minus v into u square v into 1 minus w plus u square v double plus u into AD minus BC, right? So uv square into 1 minus w plus uv double into u. And simplifying this, so we'll get is equal to u square v minus u square v square plus u square v square minus u square v square w plus u square v square w. So finally we'll get, after simplification, this is u square v. Next problem, since if x equal to e power r secant theta, y equal to e power r tan theta, then prove that j into z is equal to 1. So we are here verifying the reciprocal property of Jacobians. So but how to calculate that? First we will calculate Jacobian. J, here first it is given x and y are functions of r and theta, right? So the first Jacobian is dou of xy by dou of r theta. We first calculate j, and then we take its reciprocal as j dash, multiply j with j dash, that will give 1. So first we will calculate j. So j equal to dou of xy by dou of r theta, and j dash is dou of r theta by dou of xy. So Jacobian j equal to dou x by dou r, dou x by dou theta, dou y by dou r, dou y by dou theta. So first we calculate, right? So with respect to our theta term constant, we write secant theta as it is, differentiation of e power r with respect to our e power r. Dou x by dou theta, with respect to theta, r term constant, we write r e power r term e power r as it is, differentiation of secant theta tan theta, because with respect to theta. Dou y by dou r, same thing with respect to our theta term constant, differentiation of e power r. Dou y by dou theta, so with respect to theta, r term constant, that so we write e power r as it is. So differentiation of tan theta secant square theta. Substitute in Jacobian, z equal to, so this is, so expanding this, e power r secant theta into e power r secant square theta minus e power r secant theta tan theta into e power r tan theta. This is e power 2r, e power r into e power r, e power 2r secant cube theta minus e power r into e power r, e power 2r secant theta tan square theta. Now this is e power 2r. So for first and second, take secant theta common, secant theta into secant square theta minus tan square theta. So this is e power 2r into secant theta. Now use the property of Jacobian. So by inverse function theorem, since j dash equal to j into j dash equal to 1, we have j equal to e power 2r secant theta. Therefore j dash is reciprocal of j, that is 1 by e power 2r secant theta. And therefore j into j dash equal to e power 2r secant theta into 1 by e power 2r secant theta, which is equal to 1. Thank you.